Okay, welcome to your video lecture for section 10.7 on the wave equation, vibrations of an elastic string. Okay, so we now turn our attention to wave phenomenon, some form of the wave equation, which is kind of like the heat equation, except for there are two time derivatives here, almost inevitably arises in many mathematical analysis of phenomena involving propagation of waves in a continuous medium. For example, the study of acoustic waves, water waves, electromagnetic waves, seismic waves are all based on this equation. Okay, so we assume that we have an elastic string of length L tightly stretched between two supports on the same horizontal level so that the x-axis lies along the string. The elastic string may be thought of as a guitar string, a wire, or possibly some electric power line. And we suppose that the string is set in motion by plucking, for example, so that it vibrates in a vertical plane. We let u of xt denote the vertical displacement experienced by the string at a point x at time t. So here we have the idea here being we have one side where the string is fixed and then another side where the string is fixed. Here this is going to be x is equal to 0. This is x is equal to L. We're going to assume that this guy here is U equaling 0, and sort of if we pluck the string, for example, the displacement here, the vertical displacement at x at time t is going to be given by U of xt. If damping effects and the amplitude of motion are not too large, the string is fixed at u is equal to 0 at the two endpoints, and the initial displacement of the string is given by f, and the initial velocity profile is g, we have the following initial boundary value problem here for u. Okay, so again, very similar to the heat equation except for the second time derivative there on u, and also this second initial condition because of the two time derivatives on u there. Okay. We're going to assume that the initial displacement f is non-zero, but the string is released at time t equal to 0 with 0 velocity. So in this case, g of 0 is 0. Okay. And we're going to go through a very similar solution regime as the heat equation. We're going to assume the separation of variables assumption, which gives us the same boundary value problem for x, and a different initial value problem for t, a second order initial value problem for t. As with the heat equation, we know that the values of x at the endpoints are 0, and additionally, since we know that the initial velocity of the string is 0, we have that t prime of 0 is 0, since, because u again is written as x of x, t of t, we can't have x of x being 0 for all x without the solution being trivial. We have one initial condition for t. We know from the heat equation that the solutions, the eigenfunctions there, x sub n, are sine of n pi x over L with eigenvalues lambda n equaling n squared pi squared over L squared. So we use the lambda n's to solve our initial value problem for t. We know that t prime of 0 is 0, which will allow us to solve for one of the constants in the general solution, which is given by the linear combinations of sines and cosines. Notice, since the a appears in the equation for t, the a will appear in the solution for t. T prime of 0 being 0 implies that the second coefficient, the k2, will be 0, and thus our un's, up to an arbitrary constant, are going to be equal to the product of sines and cosines here, with the only difference being this a here in the argument for cosine. Okay? So making our solution up to arbitrary constants, this infinite series of the product of sines and cosines here. The initial profile of the string f means that we can, upon substituting t equal to 0, gain this relationship for f and our solution. And this is very similar again to the heat equation. We multiply both sides by the nth Fourier sine basis function, we solve for kn, we end up with the fact that kn is the nth Fourier sine coefficient for f. Okay, thank you.